Today we're going to look at adding probabilities together. Before we do that, I just want to go over some definitions. The first one is theoretical probability, and that is the theory behind the probability. So for example, we have a coin, and there's two different outcomes. It can land with the head facing up or the tail. So let's say I ask what the probability that the coin will have the heads facing up. Well, how many different ways can the head side of the coin face up? Well, there's only one. And how many total outcomes are there? There's two. So that's our sample space. And this is the number of ways we can receive our outcome. That's our theoretical probability. To change that to experimental, what we would say is that we're going to flip the coin 10 times. And we want to find the probability that it's a head that turns up. So let's just say, for example, we get a head, a tail, a head, a tail, a tail, a head, a head, a head, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're actually doing the experiment here. So how many different heads did we get? 1, 2, 3, 4, 5, 6, out of a total of 10 attempts. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now notice that this is not 50%. Our theoretical probability is 50%, but when we actually did the experiment, we got 60%, and that's fine because experiments don't 100% prove the theory, but they show the theory. Now, a way to get our percentage closer to the 50% is we would flip the coin more times. It's called the law of large numbers. Numbers. And the law of large numbers is saying that the more times you attempt an experiment, the closer our experimental probability will be to the theoretical probability. Two other definitions that you need to know before I get into the adding probabilities is this term of mutually exclusive events and not mutually exclusive. So mutually exclusive means that we're going to look at two different events and we're going to add them together. But if they're mutually exclusive, that means that there can't be any overlapping parts. So for example, I'm going to have my event A and event B, and we always have to define what our events are, meaning we have to define what the probability that we're trying to find, the total probability that we're trying to determine. So event A could be rolling an odd on a die. And event B is rolling an even on a die. Now the reason why these are mutually exclusive is because they have absolutely no overlapping outcomes. We draw this with two circles, and we could say that this is the probability of event A, and this is the probability of event B, where A is odd, so 1, 3, and 5, and even is 2, 4, and 6. None of those numbers are overlapping, so that's why we're calling them mutually exclusive. Not mutually exclusive means that we can have overlapping. So let's say event A is rolling an odd, and event B is rolling a number greater than 2. So let's look at our outcomes. Rolling an odd, that's 1, 3, and 5. Rolling a number greater than 2 is 3, 4, 5, and 6. As you can see, we have overlapping outcomes. So we would say that these are not mutually exclusive. How we show that in a diagram, so when we do our circles, we have overlapping circles. These are called Venn diagrams. So here's my probability of A, here's my probability of B. So for A, I have the 1 that's just an A. I have the 3 and the 5 that are in both of them. And then I have the 4 and the 6 that are left over in event B. So these are called not mutually exclusive because there are overlapping events. So when you're given a question, you have to first determine, first of all, if there's more than one event happening, and second of all, if they're mutually exclusive or not. So for this one, it says find the probability of rolling a 7 with 2 dice. So first thing I'm going to do is, and I should probably say the sum would equal 7. I'm going to make a sample space. I'm going to add these together. So my first die, 1, 2, 3, 4, 5, 6. These are my outcomes. 1, 2, 3, 4, 5, 6. Now because I'm looking for the probability of the sum, I need to add these together. So I could have the 1 and the 1, which is a 2. I could have, this is my first die, and this is my second die. I could have a 1 on my first die and a 2 on my second die. That would add to 3. I could have a 1 on my first die and a 3 on my second die. That adds to 4. You'll see that there's a pattern here. So 1 and 2, 1 and 3, 2 and 2. So all I'm doing is finding the sums of the 2 die when they're rolled together. So these are my possible outcomes. I'm looking for the probability that the sum is equal to 7. So how many different ways can we get the sum equal to 7? 6. We could roll a 6 and a 1, or we could roll a 1 and a 6. We could roll a 2 and a 5, or we could roll a 5 and a 2. How many total outcomes are there? There's a total of 6 by 6 total outcomes. So the probability that the sum is going to be equal to 7 is 1/6. Now this is an example of only one event. So we don't have to determine if it's mutually exclusive or not. The next example is a deck of cards. It says we're going to draw 2 cards from a standard deck. Find the probability of drawing a club or a diamond. Now, first of all, I need to explain some probability terminology. When you see the word or, that means that you need to add. When you see the word and, which is what you'll see in the next lesson, that means you're going to multiply. So when we're looking for a club, we're saying what's the probability of a club or a diamond? So we first we separate them, the probability of a club plus the probability of a diamond. How many total clubs are there? Well, there's 52 cards in a deck. There's 4 suits. So each suit has 13 cards. So we have 13 clubs over a total of 52 cards. And we have 13 diamonds over a total of 52 cards. So when we simplify that, we get 26 over 52, which is half, meaning that half the deck is going to be clubs or diamonds. For the last one, I'm asking for a face card. or a spade. So first of all, you have to determine if this is mutually exclusive or not. We can have face cards that are spades. So because they are overlapping, like if you think of the Venn diagram, so here's face and here's spades. So how many spades do we have? We have a total of 13 spades. And how many face cards do we have? Well, face cards are jacks, queens, and kings times 4 because there's 4 suits. So there's 12 face cards in total. But here's the problem. I'm going to put a 12 in for my probability of face cards. Then I'm going to put a 13 for my spades. All right, I'm running out of room there. So I have 12 over 52 for my face cards. I have 13 over 52 for my spades. Now the problem is, what about this overlapping portion? We have cards that are both spades and face cards. And the problem is we have counted these cards twice. We've counted them once here as face cards, and then we counted them again as spades. So in our formula, we need to subtract one set of those because we've double counted. So how many are spades, which are face cards? Because we need to subtract them. So we have 12 plus 13 minus 3 over 52. So we really have 22 over 52. Which we want to simplify, and that's 11 over 26. So here is the rule. If we have mutually exclusive, the probability of A or B is just adding them together. If they're not mutually exclusive, then we have to take A or B, we add them together, but then we have to account for the fact that we have double counted some. So we subtract A, B. So the ones that are both A and B. And that's your formula.